Good afternoon, everybody. This is the third session concerning hydrogen. I will be chairing the session. I am Professor Nicolosi, Fabrizio Nicolosi, from University of Naples, dealing with teaching aircraft design and dealing with the aircraft design stuff. So we have 4 presentations in this session. We have 30 minutes for each presenter. Basically, I think if you can stay in, let's say, 20, 22 minutes maximum, and we leave 8 minutes or even 10 for questions, it will be perfect. So I think we can start because it's exactly 30. Yeah. The first presentation will be given by Michael Kotzem concerning his education. He did his bachelor in mechanical engineering University of Applied Science in Bochum. After he did another bachelor in aerospace science at the University of Aachen, and and after the Master of Science in also in Aachen between 2020 and 2022. He was doing also some experience in Airbus during master thesis, and now, since November 2022, is a research assistant at DLR Hamburg in the Institute of System Architecture in Aeronautics, dealing with the overall aircraft design. So the floor is yours.
Yeah. Thank you very much, and thank you everyone for coming, and yeah, welcome to my presentation on the conceptual aircraft design of a research baseline with direct liquid hydrogen combustion. Yeah, let's start right away. So, of course, in conceptual aircraft design, we aim to introduce new aircraft concepts that aim for a reduction of the aircraft environmental impact to tackle the increasing effect on climate due to the greenhouse gas emissions. So the starting point for these studies are our reference aircraft, and the reference aircraft in this case serves as a benchmark representing the current state of the art technologies, so yeah, representing today's technologies. And when we have established the reference aircraft, we can think of new advanced aircraft concepts, alternative energy carriers, and also climate-friendly technologies, so that we end up with a new aircraft concept, and in our case we aim for an entry into service for 2035. Some of those new technologies might be some of the clean aviation sub-projects where new engine technologies, new wing technologies, and also new fuselage technologies are investigated. But if we apply those new technologies onto the aircraft design, we also want to evaluate the energy saving potential of those technologies. And we cannot do so if we compare them to the reference aircraft with today's state-of-the-art technology. And this is why we need to introduce a research baseline. So the research baseline is the projection of the reference aircraft into the year where the technologies enter the market, so in this case 2035, and assuming an evolutionary technological progress. And this enables us then the scientifically sound evaluation between those new technologies in terms of their energy saving potential. So that's why the research baseline is important to us to assess this. And in our case, we already had an established reference aircraft, and we also have an established SAF research baseline, including a 2035 technology level. However, as I said, we also look at alternative energy carriers, especially LH2. And since we also want to assess for LH2 technologies, we also need an LH2 research baseline where we then can later on evaluate the impact of those new technologies. And this is basically what we did in this study. It's the derivation of this liquid hydrogen research baseline. But coming shortly back to the reference aircraft, and the top-level aircraft requirements. So the reference aircraft in this case is the D239. It's an DLR short, medium-range aircraft concept with 2020 technology level. And the TLRs are the following. So we have a design range of 2,500 nautical miles. We carry 239 passengers and have a design payload of 25 tons. The cruise Mach number is 0.78, and we also stick with operational requirements that are typical for the short medium range market, such as the takeoff field length with 2,200 meters. Those top-level aircraft requirements are then an input to our iterative, multidisciplinary and multi-fidelity aircraft design workflow. There, the TLRs and also other aircraft design parameters, such as the tail configuration or the wing placement, are an input to our low-fidelity aircraft design tool that is called OpenAD. So yeah, it's a conceptual aircraft design tool based on handbook methods, statistics, and also own-developed methods. And from there on, we get an initial aircraft geometry, a mass breakdown, the aerodynamic and engine characteristics of this starting point. And yeah, this starting point is then forwarded to our mid-fidelity components, such as a more established process for a component mass calculation, where, for example, the fuselage mass is calculated in more detail. We carry out the aircraft mission analysis for the high-speed and low-speed performance, where, for example, the equations of motions are solved for each time step during the takeoff trajectory, so that we can ensure that the takeoff field length requirement is fulfilled. And we also have a LH2 sub-workflow that is structurally sizing the LH2 tanks, that is calculating the mass for the tanks and systems, and also carrying out a thermodynamic cycle analysis during the aircraft mission trajectory. All of those data is then carried in the synthesis and updated for the next loop. We do a weight and balance check, and once we have a converged aircraft solution, we carry out the post-processing and assessment, where we analyze the payload range characteristics and also do an evaluation mission analysis, which is in this case a mission length of 800 nautical miles. And having the aircraft design workflow set, we can already start with the aircraft design studies. And our starting point is the DLR F25. This is a SAF research baseline, so it already includes a 2035 technology level, such as a high aspect ratio wing. And the derivation of the liquid hydrogen baseline starts from here. But since we changed the energy carrier, we also need to assume LH2 technology assumptions, which are the following. So what we assume for the LH2 research baseline is an increase of the engine performance by 5% due to the higher specific heat capacity in the exhaust mass flow, since we burn hydrogen. We assume that the wing mass will increase by 5% since we have no relief in the wing structure due to the dry wing. And we also assume a 7% fuselage mass increase, which is mainly for additional maintenance, access panels at the tank region, a tank removal system, and also crash structures in the tank region. Short advertisement: if you want to learn more about the starting point for this aircraft, the DLR F25, you're very welcome to join the presentation of my colleague Sebastian Wöhler tomorrow at the track 5.5. Coming back to the DLH25, the LH2 research baseline we want to derive, and the tank integration. So we follow a dual tank design, which is necessary for redundancy reasons. And we also follow a rear fuselage integration as an initial integration concept. This integration concept has already been proven to be a promising tank integration in several DLR projects, especially with regard to the aircraft performance, efficiency, and maintainability. And we can also assess for the aircraft feasibility. So we only have minimal configurational changes compared to other integration concepts, such as where the tanks are located on top of the fuselage or ported under the wing. However, other tank positions will also be investigated in future studies for a complete assessment. This is then done in German-funded LUFO projects, but for now we stick with the initial concept for the rear fuselage integration. And yeah, if we look now at the SUAVE research baseline and especially the fuselage geometry with a single aisle aircraft and 6 seats abreast, and if we would like to integrate our hydrogen tanks at a similar fuselage geometry, we would end up having a fuselage length of roughly 70 meters. So yeah, this of course is not a feasible aircraft concept. This is the reason why we started then a seats abreast study where we varied the amount of seats abreast, and of course we're able to decrease the fuselage length again and have feasible aircraft concepts. We also include now the block fuel delta for each of those concepts. You see that we have an optimum there for 8 and 9 seats abreast. And in the end, we went with the 8 seats abreast configuration due to the block fuel efficiency, the landing gear integration, but also the fuselage accessibility for ground operations. So this was one part of the aircraft design studies. The fuselage geometry was set. Another one we carried out was concerning the insulation architecture. So we looked at 2 options here. One, the closed cell rigid foam, and the other one, the vacuum MLI. The closed cell rigid foam being a more lightweight solution, already widely used in space applications. However, having higher heat leaks compared to the vacuum MLI. So the vacuum MLI with better insulation capabilities, but due to the second sealed compartment, it has a more complex structure and that is therefore more heavy. To be able to compare those 2 architectures with each other, we introduced the dormancy time requirement. So this dormancy time requirement in this case means or describes the period of time after landing during which the aircraft does not need to vent hydrogen on the ground. So yeah, in this case, it's a post-flight dormancy time requirement. And since the foam insulated tank is particularly affected by this requirement, we carried out a local sensitivity study for this insulation architecture, where we increased the dormancy time between 4 up to 8 hours. Yeah, and where the foam thickness of the insulation architecture was always adjusted automatically, so that the dormancy time requirement is fulfilled at all times. And the results I will show you here. So what you see here is, as I said, the variation for the dormancy time between 4, 6 up to 8 hours. And then the impact on the delta of block fuel and OEM compared to the MLI insulation architecture. What you also see and what we also varied is the maximum operational pressure of the tanks, since this parameter is also influencing the potential delay until the venting of hydrogen is necessary when you're on the ground. So there we varied between 2.25 up to 3 bars. And I hope you see it with the colors, but what is quite interesting, or what we found out, is that here for the 4-hour dormancy time requirement with the 2.25 bar tank, so the lightest tank, we have the best performing architecture concerning the block fuel, and we also have on the right hand side the lightest aircraft design with respect to the OEM. However, if we increase the dormancy time requirement, this architecture becomes the worst performing, and it also becomes the heaviest with respect to the OEM. So you cannot see the points there, but that's why I used the mouse here. But yeah, it was interesting to find out that there is some kind of tipping point for the aircraft performance if we vary those parameters. And why is that? So due to the increase of the dormancy time requirement, the foam thickness of the tanks became so thick that the tanks increased in length so much that the overall aircraft length became so long that in the end the OEM went even higher than that for the more heavier tank with 3 bars. And based on DLR studies where the ground time events and their duration was studied and analyzed, we decided to go with the 6-hour dormancy time requirement. Everything more than 6 hours is for us then supported by ground systems at the airport, or its airport infrastructure. For the 6 hours we had then the best performing architecture with the closed cell rigid foam and a maximum operational tank pressure of 2.5 bars. And the foam thickness there was then in the end 14 centimeters. And this already leads us to the results for the LH2 tank design. On the right hand side you see the geometrical constraints we implemented for the tank design. So we have 1.5 meters of geometrical spacing between the tanks for the integration of the cryogenic systems. And we have 0.5 meters on the lower side of the tanks to the fuselage to have sufficient spacing for the integration of crash structures. The 0.2 meters on top are then for the fuselage frames. On the left-hand side, concerning the mass values, you see that we have a total structural mass for both tanks of 5.6 tons, 730 kilograms of systems mass, and a maximum usable fuel mass of 6.5 tons. This leads us to the gravimetric index, which is, if you only consider the structural mass of the tanks, to 54% and to 51% if you also include the systems. If we compare the top view of the final LH2 research baseline, the DLH-25, and the reference aircraft, the D239, you already see that we did not only needed to increase the cross-section of the aircraft, but we also needed to increase the fuselage length. Furthermore, you also see that due to the high aspect ratio wing, we were not able to integrate the landing gear in the wing anymore and had to switch to a body-mounted landing gear. And if we look here at some key numbers, you can see we have roughly the same maximum takeoff mass, but have a significant increase of over 10% for the maximum landing mass. This is mainly due to the difference in the fuel weight, since we have different energy densities for kerosene and hydrogen. The OEM also increases significantly by over 20% due to the integration of the heavy tanks and also the changed fuselage geometry. And if we look at the block energy performance, we see that for the design mission of 2,500 nautical miles, the LH2 research baseline is 0.6% better performing than the reference aircraft. However, for the evaluation mission, we have 5% higher block energy consumption for the LH2 research baseline. The wingspan was based on the SUAVE research baseline increased to 45 meters, increasing also our wing aspect ratio. And what we also needed to do is to heavily increase the wing area, since we stick with the same top-level aircraft requirement for the approach speed and the higher maximum landing mass. We needed to increase the wing area here. As you can see, fuselage length was then in absolute numbers an increase of 7 meters. The engine performance was then already mentioned during the LH2 technology assumptions, and the LOVD during the mission is roughly the same. We also analyzed the overall aircraft sensitivities, and here we compared them to the SUAVE research baseline. So in the end, we found out that if we increase the TSEC for the DLH-25, we have a 1.8% increase in block energy and only 1.16% increase in block energy for the SUAVE research baseline. We also did that for the aerodynamic drag and the mass, and there we saw, especially for the drag, the same, that we have a higher sensitivity for efficiency changes for the DLH-25 compared to the DLR F-25, so the SUAVE research baseline. And why is that? So we have a closer link here between the aircraft efficiency and the geometry. There's a more intense coupling. So if we have a worse efficiency, we not only need to carry more fuel, we also need to increase the tanks, and this directly influences our fuselage geometry. And of course, we have tanks integrated at the rear of the fuselage, so we need to check our weight and balance diagram. And here you see the loading sequence for the design mission of 2,500 nautical miles. And as you see, the center of gravity positions are in accordance with all limitations during the loading sequence. But if we want to fly with low payload or carry out a ferry flight, you see that we are not in accordance with the limitations anymore. So for these cases, we need to carry ballast with us so that we counteract this and stay within the limitations. And in this case, it's roughly 7 tons of ballast that is needed for a ferry flight. And to conclude this, we derived a reasonable hydrogen aircraft concept for the short medium range segment for 239 passengers and an entry into service for 2035. We needed to increase the fuselage cross-section diameter to be able to integrate the hydrogen tanks into the aircraft. Furthermore, we analyzed the impact of the dormancy time requirement on the insulation architecture, but here we can say that both MLI and rigid foam are reasonable options. And we found out that the hydrogen concept is more block energy sensitive to changes of the overall aircraft efficiency than a kerosene aircraft. Concerning our future work, what we want to do is to bring more fidelity into this aircraft design. So what we want to do is to have a higher fidelity wing mass analysis. We also have a cut geometry and want to carry out CFD analysis. We want to integrate a higher fidelity engine design, and what we also want to integrate is a system architecture that is tailored for this LH2 aircraft. And that's it. Thank you for your attention.
Thanks. Are there any questions? We have 9 minutes, so.
Hi, excellent presentation. Jimmy Tai from Georgia Tech. Is your tank pressurized for the LH2 tanks?
Yeah, it's a pressurized tank.
Okay, and in your mass accounting, do you account for the, I guess, the pressurization and pumping that's needed to keep that tank pressurized?
Yeah, we account for this.
Okay. And I guess, can you tell a little bit detail about higher fidelity engine modeling that you're planning on doing next round?
So what I can tell you is that we at DLR have institutes that specialize on certain topics, and that we will collaborate with our engine design department, which will then carry out a higher fidelity engine design. But as I see the colleague is also sitting here, you might ask him afterwards. I can introduce you.
I was just curious whether you're going to go beyond the cycle, maybe like a mainline code for the turbo machinery or anything like that for the next round.
I didn't hear it, no.
That's fine. Thank you. Excellent work.
Okay.
Other questions?
About the configuration of this plane, I understand that if you put the tank in the middle, you need to have 2 doors for the passengers and 2 areas for the passengers. But with this configuration, do you have study the mass and CG? Because when you have no passenger, you have a lot of mass in the rear. Just to understand if you have studied about this configuration and the mass for the airplane.
So for this concept,
Yeah.
we carried out the weight and balance analysis. And as I said, if we have if we have no passengers and want to have a ferry flight, we have issues with this topic because we have then a huge of mass at the back of the aircraft, and this is why we need the ballast. So for these missions, we need to counteract with ballast we put at the front of the aircraft. It's roughly 7 tons, so that we can stay within our limitations. Yeah.
I have a consideration concerning it's interesting to see that your results, of course, we have, at least I have noticed that, of course, the solution has problems concerning weight, and so the gain can be really limited. In addition, there is a consideration concerning, for example, wingspan. You go on a single A class, you go from ICAO C to another, because the span is higher than 36 meters. So on the airport, there will be completely different operation for this kind of airplanes, which will be more similar than, let's say, on a A350 or Boeing 787.
Yeah, that's right. So we increased the span going over the 36-meter limitation, but this would then be a potential use case for foldable wingtips, and then you could stay within the limitation of the 36 meters.
Other question? Okay, if not, thanks again to Michael. Very interesting topic. We will wait 3 minutes just to respect the time. Just I want to highlight that yesterday in the PC they told that you should avoid to make any picture. So please, maybe it's just because there is an indication of ICAS committee that let's say picture during presentation are forbidden. So we can go to the next presentation. The presenter is Andrea Battiston. He was taking master in aerospace engineering at the University of Padova, and now he's a research engineer at IT09, which is a spin-off company of Padova University, which is active in simulation, design, optimization, and code development for not only for aerospace but also for energy engineering. And topic, let's say, specialized topic for Andrea are aircraft aerodynamics, optimization, and CFD. The presentation will be design optimization of a boundary layer ingestion propulsor for a multi-fuel hydrogen aircraft. The floor.
Okay, thank you. Good afternoon, everyone. As said, this this presentation will deal about design optimization of a BLI propulsor for a multi-fuel hydrogen aircraft. So. Okay. To briefly summarize the concept, the design came from a European Union funded project called HOPE, and the concept is to unify 2 concepts, which are ultra high bypass ratio turbofan engines plus a fuel cell power boundary layer ingestion propulsor. And yeah, I think the name HOPE is quite fitted for this kind of project. The top level aircraft requirements are listed in the table at the right-hand side, and as you can see, the aircraft is a A320 scale concept in terms of dimension and range. And the idea is to, as I said earlier, utilize 2 concepts of engines. the BLI propulsor to enable a zero-emission taxi and to aid the turbofans in cruise conditions. Also, ultra-high bypass ratio turbofans with the capability of using a flexible burning of mixtures of kerosene or sustainable aviation fuels and hydrogen. The present study, as I said earlier, is focused on a preliminary sizing and mostly in the design and space exploration of the BLI propulsor. In order to have a rough idea of the fan power of this propulsor, we took the PAC, the power saving coefficient, which was a parameter introduced by Smith in the topic of the boundary layer ingestion propulsor, and as a figure of merit to determine the main geometrical features and the fan power of the fuselage. The ideal shaft power is evaluated using a non-dimensional heuristic equation for the propulsive fuselage efficiency vector, and I cited a work from a partner of this project, which digs more in detail in the topic, but I will recall the equation in the next slide. Two analyses were conducted. The first one was used the fuselage length as a design variable, and the second one introduced variation in the fuel cell system efficiency of the auxiliary power and propulsor unit. As you can see, the power saving coefficient is defined as this ratio between the delta in the reference power of a reference aircraft and the propulsive fuselage concept power over the reference power. And the propulsive fuselage concept power is evaluated as the useful power comprising both the bare wall forces and the fuselage fan force considered in this preliminary investigation as an actuator disk. These studies gave us the possibility to determine for different lengths and different fuel cell efficiencies a range of shaft power which lies between 2 and 4 megawatts for this case. So we decided to stick in this range. As a reference model, we decided to reconstruct a model based on the 320 neo fuselage, and we decided to also add a scaled fairing from the CRRM model, mainly for two reasons. The first one, we did not have the cut for the fairing, and second one, we needed to not have a coordinate separation at the wing root, because the flow that goes downstream will be ingested by the fan, and we wanted to avoid separator flow ingested by the BLI propulsor. In terms of performance evaluation, as you may know, it's difficult to use a momentum-based approach for a BLI propulsor, because the strong integration between the fuselage and the propulsor does not permit to define a consistent way the thrust. So we decided to start from a momentum approach and make some tricks. We firstly defined the net assembly force of the overall airframe, as the sum of the total wall forces acting on the airframe plus the gauge forces at the BLI fan cross-section, exit and inlet. From this one, which considering also the podded engines should be zero in cruise condition, but will not be zero in this case because we did not consider the underwing engines. We define a surrogate net propulsive thrust by taking the difference between the net assembly force and a reference drag that is being evaluated from the previous CFD on the reference model. And this surrogate net propulsive thrust should take into account the differences both in the shape of the fuselage that are needed to install the propulsor and also the effect of the fan. From this surrogate thrust, we define finally the surrogate propulsive efficiency by taking the surrogate thrust power over the fan power, and this will be the metric that will be used for the design investigation and to make all the conclusions. The parameterization has been done in a three-dimensional way by considering three azimuth profiles, which are defined in a 2D space, and then by defining interpolation laws between the three profiles. For each section, continuity with the at least tangency has been granted, and we also define as a further design variable the leading edge curvature radius while using Bezier curves so that this curvature radius guides the vertical position of these 2 points given the position of these two, and permitting us to use simple curves with a class C2 continuity. In terms of mesh, we decided to go for a multi-block mesh, which is comprised of a structure region for the wake and the propulsor, and an unstructured region for the outer field. The surface meshes are all quad dominant or structured, and as you can see from the convergence analysis, the resulting mesh is about 51 million elements. This, considering that we simplified the model, not considering all the tail, but just the vertical tail plane, and not considering the presence of the underwing engines. So it's worth noting that this design investigation is based on a simplified model of this aircraft concept. The design of experiment has been carried out in cruise condition, and a Latin hypercube sampling has been considered for determining the population using 50 individuals. It's not a very high number of individuals, but considering the overall computational costs of the CFD, it was a trade-off between the time that we had at our disposal and the results we wanted to achieve. The objective of this DOE is to down-select the most influential variables of on the propulsor performance and obtain baseline configurations that will be used for further optimizations. As I said earlier, the target performance are the net assembly force and the surrogate propulsive efficiency, which were defined in the previous slide. This is the list of all the design variables that were varied during the design space investigation, and the most interesting in our side prior to the exploration were the nacelle cone angle and also the nozzle contraction ratio, the hub to tip ratio, and the fan total pressure ratio. The results are summarized in this graphic, which is a linear correlation plot. In short, you have to read this plot by taking, for instance, this cell, which is the correlation between the hub-to-tip ratio and the mass flow rate, and the slope and color saturation represents the linear correlation values between the two variables. And of course, in red, it's a descending correlation or an increasing correlation in green. You can see from these results that the surrogate propulsive efficiency is highly influenced by the nozzle contraction ratio and has a low correlation on the hub-to-tip ratio, while at the same time it guides the net assembly force, the shaft power, of course, and the mass flow rate, because by increasing or decreasing the fan size, we will have, as an outcome, a different amount of mass flow rate that is ingested. Other variables which were interesting but did not have a very high influence are the axial length of the nacelle, and it's quite interesting, though, that fan pressure ratio does not have a very high influence on this performance. This is mostly because we choose to keep the boundaries of this variable very strict, and by varying the fan pressure ratio between 1.3 and 1.4. Therefore, we were in a very small region. This was done based on our previous knowledge on a previous project in which a simplified design exploration led us to understand that an optimal region for this surrogate propulsive efficiency lies within this range. So we thought that would be a waste of computational effort to investigate outside this boundary. As an example, these are the influence plots for the hub-to-tip ratio and the nozzle contraction ratio, showing that there is indeed a certain amount of correlation between the variables, and recalling that this one has the highest influence on the propulsive efficiency. This is the best individual from the DOE, and as stated in the slide, we focused on refine this shape, mostly in the highlight region, but most importantly to optimize the flow expansion of the nozzle for a stable operation of the fan. After an optimization, this is not part of the paper, but we we concluded that work recently. We found out that there is, with an optimization and increasing in the efficiency, this should be the propulsive efficiency of about 2.4%, while increasing the shaft power, but lying it in the range of 2 to 4 megawatts. To conclude this, as stated earlier, thank you. To conclude, this project aims to develop a multi-fuel hydrogen-powered aircraft with a BLI propulsor. And we define an initial configuration for the aircraft and the BLI. This configuration will be further carried on. But this design space exploration was important to define the most influential variables. And to determine a preliminary shape. the aircraft will be completed with a detailed design of the power plant for the ultra-high bypass ratio turbofans. Also, the hydrogen fuel cell BLI propulsor, and currently we are dealing with the design of the fan based on a model which relies on a parallel compressor theory. This study, as said earlier, is financed by the project HOPE, which is part of the European Union Horizon program. Thank you, and sorry for the cough. Thank you.
You have been very short, so
Yeah.
we have a lot of time for questions.
Yeah, I noticed.
You've mentioned optimization several. Oh, thank you so much. Great. So thanks for the talk. You've mentioned optimization a number of times, and I wanted to know more. Which optimization methods did you use, and about computational tractability, computational times?
Okay, I did not go in detail in this topic because it was not initially part of this paper, because we end the optimization after the deadlines. So it's our plan to talk about it in more detail in next. In a further occasion, but to be short and precise, we used an optimization method based on a genetic algorithm. So by defining from the DOE a smaller range of the design space, we follow up the design by putting the model inside the genetic algorithm.
And maybe you can also consider Bayesian optimization, which has become more and more effective, but we can talk about it offline later. Yeah.
You're right. The point is we use a proprietary tool for my company. So, yeah.
Yeah. I don't know if my question is reasonable, but have you compared your result with the Aura concept from MIT? Is like your gain in efficiency is consistent with their results, or?
Yeah, it's difficult to compare results because of the fact that there's the problem is you cannot define trust, and therefore the figure of merits that are used in the BLI are not consistent between the projects usually. So each one used their own, and it's difficult to compare numbers using different approaches. So yeah.
Is there any experiment planned?
We plan after the design will be finished to downscale and produce a series of wind tunnel test experiments on that, also considering the noise.
Okay, thanks.
You're welcome.
Other question? I have just curiosity concerning the which CFD solver.
ANSYS Fluent.
Sorry?
ANSYS Fluent.
ANSYS Fluent.
Yeah.
No other question? So, thanks again, Andrea. Thank you. Okay, I saw there were some people joining, so it's good to. We have waited till 5:30. So the third presentation in this hydrogen session, number 3, is the Christian Svensson. He was taking the bachelor in mechanical engineering at Chalmers University in Göteborg, Sweden, and master in applied mechanics at the same university, Chalmers, between 20 and 22. The thesis was on design and evaluation of a manned air vehicle system. And now he's currently PhD in fluid dynamics at Chalmers University. The topic of research activities of Christian are search and rescue of a manned vehicle, turbulence modeling, CFD, and multi-phase flows. And he has passion for developing aerodynamic solution for motorsport. So, but I think you will be, yeah?
Yeah.
Your presentation
There'll be no cars here
aircraft.
today. Yeah. Right.
Or is yours?
So can you hear me? Thank you for a nice introduction. Yes, I'm Christian. I'm a PhD student at a competence center called Tech for H2. It's a bunch of companies in Sweden. We're working towards a hydrogen economy. But yes, I sit in the fluid dynamics department. With me in the paper, I have my colleague Petter Miltén and my professor Thomas Grönstedt as well. They could not be here, unfortunately, but let's move on. Little bit of agenda. I'll start with a why. So why are we interested in fuel cell aircraft, these kind of short range to regional ranges? Next, what are the challenges for this? Why is it a bit difficult? Why are we even looking into it? Like if it worked, we would have flown with it already, so yeah. And then a bit more boring stuff, the implementations into SUAVE, which I'll talk about more later, but it's open source conceptual design software. Then we'll go a bit more deeper into the methods, not too much equations, I promise. I think there might be one actually, which is a record in low amount. But yeah, storage tanks, of course, for the liquid hydrogen, how we dimension the fuel cell systems, and then when we actually try to fly the aircraft virtually, what are the dynamic models involved? And lastly, how we resize airframes to make the simulations representative for a future aircraft. Lastly, the most fun stuff, I think. I'll have two results, basically. First, I'll show a bit of considerations when sizing tanks and how many tanks you want. Then we'll do a full sizing of a ADR 42600 or a redesign into a fuel cell. And then lastly, I'll talk about a specific case we investigated in the Nordic market. So how would a good airplane look for the Nordic market? But let's begin with the why. So why do we want to push for fuel cell aircraft? So if you consider a global airport with the departures, the regional aircraft produce 80% higher CO2 intensity than larger classes. And of course, if you don't know, intensity just means the kilograms of CO2 normalized by passenger kilometers. So that's quite bad. A third of the CO2 emissions emitted by these departures are then attributed to these below 1,500 kilometer flights. We know in the future, and you hear a lot of different proposed technologies here, it will be a mix. So we definitely have to try to look at different things, and we find a spot for fuel cells in the lower ranges. Basically, we come in where the batteries fall off. And then we think shorter ranges is a perfect proving ground for technologies, both for the aircraft and for the infrastructure. It's lower risk, lower costs involved. Okay, so why is this so damn hard? If we start off with the fuel storage, a very key number or metric that we use is the gravimetric efficiency, or GI, or index. So in the equation, I think this is my only equation, we see it's mass of fuel divided by the total system, so fuel and tank. And studies have shown, quite simple studies, but still valid, that if you want to beat a conventional regional kerosene aircraft in energy, so you want to use less energy, you have to have tanks that are able to exceed 45% of GI. Another consideration is installation. Hydrogen is hard to store in the wings unless you do some very slender tanks, but you don't want to do that for structural and heat transfer reasons. You try to keep it as spherical as possible, sometimes cylindrical. And then, of course, for the short ones, if you want to save money, maybe you want to put them just in the rear where there's some space, but then you have to care about COG shift while flying. And then lastly, the whole problem with cryogenic hydrogen in tanks is how do we trade insulation that affects the boil-off rate versus the tank weight. And the main driving factor in tank weight is actually the ventilation pressure you set. So that's the pressure at when the hydrogen is cooking, you increase the pressure, and then at some type of pressure, you have to start ventilating. That's the P-max, as we call it. Moving on to the other part, the fuel cells, also a bit difficult. It's always which is harder, I don't really know. Maybe the tanks. But big thing with fuel cells is the heat management. So usually you say that fuel cells have 50% efficiency, which means if you produce a megawatt, you also have to cool it off a megawatt. That might work for different type of engines. Here it's quite hard. Big thing is the low operating temperature. So 80 degrees is kind of standard, has been for a while. Now they're pushing more up to 120 degrees Celsius. But this makes the delta T very low for especially a hot day takeoff. So you need quite large heat exchangers, and they might grow very big and heavy and draggy. Installation, of course, where they put all the auxiliary components or balance of plant, as we call it, compressors, humidifiers, cooling fans, cooling pumps, etc. And then you also have to integrate this cooling duct, which houses this giant heat exchanger. So just for reference, this is the now defunct company Universal Hydrogen. That's a -8 de Havilland. And you see quite a large radiator. Maybe you think the frontal area is kind of the same as a Pratt & Whitney turboprop, but you see it's much longer. So the stacks and the auxiliary components take quite a lot of space. Okay, so last slide on the intro. SUAVE stands for Stanford University Aerospace Vehicle Environment. It's a tool where you can conceptually design aircraft, do trade studies, etc. So what are the benefits? So I'm doing free advertisement here, so I hope they pay for a trip or something. It's open source in Python, so there's great opportunity for collaboration. There's a mix of different methods you can use already in the software, and you can also add different levels. So everything from physics-based mission solvers to weight correlations, other statistical methods. And then this makes the software multi-fidelity, which means you can actually get a lot of detail on the important stuff and then save time in others. So you can have quite large optimizations with not too much loss of detail. And then, of course, you can look at tube and wings, or I was in the big auditorium today, there was a lot of blended wing bodies. You can do that as well. So what are we adding, or what's this paper about? It's first design methods for the tanks and the fuel cell systems. Then just a routine for resizing the airframe. So it's actually representative for that weight. And then some methods for the storage and the fuel cells while trying to solve a mission or trying to figure out the fuel burn. Right, so let's go into some methods. So in this implementation now, we have focused on non-integral MLI tanks. So MLI stands for multi-layer insulation. It's similar to what you have in spacecraft. You have those gold foils. That's a radiation shield. Problem here is that we don't have space. We don't have vacuum. So we have to create our own vacuum to only have radiative heat transfer. You do this by having a double wall tank, which you see in the schematic here. So inside the fuel, inner tank, that's subjected to internal pressure. Then in the vacuum jacket with the radiation shields, and then a outer tank wall to contain the vacuum. And then that's very sensitive to buckling due to external pressure. So what we do, given a number of tanks, a total fuel volume you want, a ventilation pressure, as I talked about before, number of insulation layers, gas haulage, we start by initially just calculating what that resulting gas versus liquid fraction is. Then we size the inner wall using pressure vessel codes for the internal pressure. Then we add the insulation. It gets a bit thicker. That's a correlation-based method. And then 4, we again use pressure vessel code, but this time against curved panel buckling. And then you have a tank. Problem is, you cannot always fit the spherical tanks in your fuselage. You can always make the fuselage bigger, but sometimes you just want to do a simple redesign. So if we cannot make a spherical tank, which is superior, we set the outer radius to the maximum of the fuselage, or 92% is our assumption we can use. And then we add a cylindrical section. Then for the fuel cells, multi-stack. So first, what is a multi-stack? So fuel cells are connected in series to produce a certain voltage. Then you get a stack. Then to produce the proper power you need, then you have to parallelly couple stacks to each other, and then you have a multi-stack. So given a polarization curve or a fuel cell chemistry, a wanted max propulsive power, a system voltage, and number of stacks, we first have to choose a design point on a polarization curve, and that sets the, then at max power, your efficiency, cell voltage, and current needed. Once that's done, we can get the full stack count, or cell count, sorry, by having the by knowing the system voltage and the cell voltage. Then to get the required power in each stack, you simply just size the cell area to what you need. Of course, in a system code you can do anything, so we try to keep it reasonable. If the cell area grows too big, like bigger than what companies offer, then you just add another a stack to the multi-stack. Then of course, I talked about auxiliary power or systems. So when I talk about total or system power, that's propulsive plus these compressors and stuff. Lastly, cooling system. We have a quite simple method for getting performance and sizing. It consists of a subsonic intake, a diffuser duct to slow the air down, a heat exchanger, that's where my colleague Petter Miltén has a concept code for, then a nozzle and a puller fan when the mass flow is not enough. So given a design point and a mission that you size your system for, we can then figure out the total mass flow needed, which is the fuel cell mass flow to do the reaction, and then also for the cooling. Then we size the diffuser duct, get the inlet conditions for the heat exchanger, run the heat exchanger code. That will then set the length, porosity, type of fin, etc. That's done via optimization. And then you have a full system. Big caveat here is that you need to size it in conjunction with the fuel cell system, because of course, if you increase pressure losses here, you will need stronger components in your balance of plant. That requires more power than in your fuel cell stack, which raises the heat. So you have to find some kind of convergence here. Okay, so we've built the plane. Now we're trying to fly it, see what the fuel burn is. So for that, we need some dynamic models, we call it. It isn't that cool. Storage tank, we do internal and external heat transfer analysis using correlation-based methods. We keep track of the liquid gas fraction and the pressure inside the tank. And then also finally, the most interesting thing, we calculate the necessary ventilation rate in case the pressure reaches the maximum. For the fuel cell, the balance of plant code is depending a lot on altitude and speed, of course, so that's considered. So you have varying degrees of air compression. And then we have the heat exchanger code as well. So here's how it can look like as a typical mission profile. In this tank, the pressure actually steadily rises until it goes to a maximum allowed pressure, and then we have to start ventilate, which is then the mass flow gas. Lastly, on methods, aircraft resizing. So here's our little scheme. I've talked about driveline definition, and also then you have to define the vehicle you want to rebuild. So in this case, an ATR maybe. You set some sizing rules. Do you want to keep the power to weight ratio, for example, or let the optimizer try different things? Then when we have the tank size, we extend the fuselage, or remove seats, depends on what you want to do. And then we go into the sizing loop, where we're interested in seeing the weight and center of gravity converged. At that point, we're done. So it's a continuous thing until you have a plane that can fly. Then now, results, I think that's the most fun. So let's talk a bit about storage first. So interesting thing, we just wanted, this is a method paper. I don't want to give away the best stuff for this conference, unfortunately. That's probably in a journal paper later, so you can stay posted. But we did some interesting stuff anyway. Number of tanks versus GI. So GI is how efficient your storage system is, right? So what's the effect of, if you have a fuel volume and you have one tank, what's the effect on the system performance if you split it into two? So here we have GI versus total fuel volume. We have a set fuselage radius that you cannot exceed. So we see that we start quite high, around 50%, depending on your Pmax. And then there's a sharp drop-off. What happens? That's when the code has to go to a spherical, or from a spherical tank to a cylindrical tank. So you lose quite a lot of performance. And then two tanks, you can kind of stay at high GI or spherical tanks forever, because you won't need 20 cubic meters of fuel from ATR. And then three, the same thing. So yeah, conclusion here, spherical tanks are clearly superior, both in structural and heat transfer considerations. And this is because the cylindrical tanks are sensitive to buckling, more sensitive to buckling, rather. So it can be beneficial to increase the number of tanks. Okay, but splitting fuel volume, increases GI, might be worse for packaging. I think it is. You have a lot more dead space inside the aircraft, so that's worse. But then maybe the biggest thing is that the total heat transfer rate for the same insulation system will go up. So there's a big trade there that you have to consider. Next, this is the penultimate result. We do a little resizing. A lot of numbers are going to come. Don't look at them. I'll try to guide you through them. So we design it with a 6 cubic meter tank, total fuel volume, sorry, over 2 tanks. Pmax 2 bar, 15 radiation shields. We do not change the power to weight or wing loading. We try to keep the runway compatibility the same. We keep the wing aspect ratio and taper, so we're just going to scale it in reference area. And we also don't mess around with the volume coefficients for the empennage. So immediately, if I will point a bit, fuselage length has gone up with 4 meters, so it's quite a long plane now. We kept the diameter, and then maybe wing reference area changed slightly with 3 more square meters. More interestingly, it's of course with these planes the weight. They get heavier, because fuel cells are quite heavy compared to a gas turbine. So that increases significantly. Of course, with hydrogen planes, the fuel weighs nothing, so you're going to land at practically the same weight, especially for this aircraft with so little fuel. Yes. The tank, 2 tanks, only weighs 300 kilos, so yeah, that is nothing. But then, of course, we've assumed quite efficient tank system. But the big thing here is, or what to consider, is the center of gravity shift fully loaded with fuel, without fuel. Of course, if you're without fuel completely, that's really bad, so you might not end up at 5.5% shift of 0 to G. That should be within the airplane's trimmability, but of course that will affect how you can load the actual aircraft. So that's a big drawback with having tanks just in the rear, even though it's easy. Then change in planform. So we have the baseline ATR-42 with a redesign then. We have scaled wing to match wing loading. The tanks require, as I said, 4 meter stretch, so the empennage now is quite far back. Wing is shifted rearward slightly. We have kept the passengers in the same place, so we just extended and put tanks behind. Very interesting thing is that, because of that then, is that the tail surfaces end up actually being smaller, which is good for drag. And that's just because the lever arm distance between the main wing and the empennage has increased. So this will almost always happen with these planes because the fuselage extension outgrows or outpaces the weight shift back, so you don't have to move the wing back at the same pace. Okay, final result. most interesting, I think. So this is actually not from the ICAS paper. This is from a journal paper we made with my professor, Thomas. It's called Sizing Aircraft for Nordic Market. So Nordic air travel, as you might know, is a bit different. This is a map. If it's a red dot, there's more people living there. As you can see, there's a lot of black dots, and it's a large distance that needs to be traveled if you're going from south to north. So we have very few airports, and they're very spread out. Very interesting thing, I was in the auditorium before, like I said, and then I think it was the Boeing guy, yeah, not being negative about hydrogen, but speaking of how difficult it will be to actually supply aircraft. He had an example of Heathrow. But then imagine Sweden. If we have a small town of maybe just a few thousand people on a runway, will they have a hydrogen gas liquefier there? Probably not. So if you can't solve it with trucks, it's very hard. So because of this and like early adaptation of this airplane, we want to look at a very special mission called Return Without Refuel. So the idea is that you fly from A to B. You land, get off your passenger and cargo. Then we are not going to refuel. We're going to stand on the ground, wait for the next passenger load, and then try to fly back to A. So this is typical. If you fly to one of those black dots, you have to go back to Gothenburg, for example. Reserves, we only included it in the flyback because if the reserves have to be used in the first flight, something's wrong, you probably have to cancel that flight operation. So we designed 4 tanks. So we've just done simple variations here. 4-bar ventilation pressure, so a heavy tank with 2 different insulation thicknesses and a lighter tank. And the 1.6 bar Pmax tank was the optimal for the nominal missions, just going 1,200 kilometers. But we will see what happens here. So this was the optimal. So on the graph here we see the range, and range here is A to B. So if you're flying the whole mission, then back as well, it's going to be double. So you see the best initial range for the optimal tank. But then there's a sharp drop-off after approximately 1 hour. So you can stand 1 hour on the ground without losing fuel. Best initial range, but yeah, it has to ventilate quite early. And this is due to the low ventilation pressure. The tank walls cannot be allowed to take too much pressure, so you have to shoot it out. The heavier tank is the blue one, which is a bit interesting. So lower initial range, but the range line is completely flat for almost 6 hours, which means you can, if all your passengers are late, that's fine. And then it has the same drop-off rate as the optimal because they had the same installation system. So a bit lower initial range, no range loss up until 6 hours. The rest of the tanks, low insulation or low ventilation pressure, not feasible. You lose a lot of range quite quickly. So then you have to fly to an airport where you can refuel. So maybe the conclusion here is the heavier tank, although it's worse for fuel burn, it might actually be the best type of tank you can have for feasible operation in the early stages of rolling these airplanes out. And with that, I open for questions. Thank you for listening.
Let's see, is there any question?
Hi.
Oh.
Hello.
Radimir Jane from Technical University of Braunschweig. I have one question regarding the mass and volume, and also your design point. Okay, there are 3 questions, but they are somehow related to each other. How did you model the mass and the volume? What methods did you use for balance of plant? Okay, the stack, basically you take some design performance, but also the other question is redundancy for your results. So did you size basically both of the fuel cells? So can you fly with just one fuel cell in your case? And did you account for this in the masses, because this will increase the mass enormously, it will increase the drag enormously, but very much, and the drag will increase, and this is a loop when then basically your convergence point may be, I don't know, 15 to 20% higher mass, and how you do it, yeah.
Yep, great question. So first question, the weight, it's a lot of numbers not included. I have some here if you want to chat later. It's quite a simple model. So the fuel cell chemistry is from a NASA technical report. So it's actually upscaled automotive fuel cell chemistry, or it's the same fuel cell chemistry, of course, then we extrapolate it and add a lot more cells than what you would have in a car or a truck or a bus. And then it was also included there a cell porosity coefficient and a cell density, practically. So it's based on an actual fuel cell plate, and then it's just scaled up. So that's the method there. So no correlation-based method there, although things might not scale as you want. We haven't looked more into that. Second part, redundancy, no, we haven't. You could probably, no. If you play around a bit with the wing loading, maybe you can do it. I think these planes are, the ATR-42, we matched the power to weight ratio, remember? It's a bit overpowered. I think the ATR-72 has similar power, but is much heavier. So maybe I was lucky and I ended up with a plane that can kind of fly with one engine operative. But no, it was not considered in this exercise.
I have a curiosity concerning the modification on the SUAVE have been implemented by you or by the let's say, the developer?
It's me.
You.
So yeah, it's not on GitHub or anything. I have to clean up the code a bit. There's some explicit language in the comments, you know. But yeah, it's our code. Nothing groundbreaking, but there was no fuel cell methods available in SUAVE, which was kind of bad. There's a lot of people asking for it, so we decided to do it. So it's a really nice software otherwise. We had many options to go for PaceLab, commercial stuff, or this.
Yeah, interesting. However, I think the tricky stuff for fuel cell, especially for fuel cell, but also for batteries, the detailed analysis of the mission. So it is needed to simulate the mission every 1 minute just to see the state of, let's say, of the current intensity and.
So that's the nice thing. We get that for every minute. Okay. And it's all connected. So if you have to ventilate gas, that affects the overall mass of the vehicle as well. So there's a lot of interconnection.
Actually, I was surprised. We did the same on the ATR-42, but the weight were a little bit different. And also, you should take into account the extra drag coming from the air intake for cooling, for the fuel cell cooling.
Yes.
Yeah, which is quite big.
Yeah. No, of course. It's there's some guesses here and there. We try to do our best, but with any system code, it's you try to make it as representative as possible. We focused on air compression, so weight might be higher in reality.
Very good.
Yes.
Thanks.
Thank you. Oh, there's one more question, maybe, if there's time.
Oh, maybe, yeah, very short, because we have just 1 minute.
I have a small question. Something you said in the end is a bit stuck in my head. It's about the small villages or towns with the one runway. Currently, when operators are going there, are they fueling for a return mission, or do they have access to kerosene there? Do you know that?
Yes, how small, it depends on how small it is. If we take Gothenburg, is our second largest airport, so of course you can fuel anything there. And then we have like a bit smaller one, Trollhättan, 1 hour away. You can, it's only very small aircraft operating there now, like turboprops. You can of course refuel there as well. So we're thinking about more rural stuff, but that's maybe not the thing. It more is, it will cost so much for society to bring this infrastructure out that large airport hubs will be prioritized in the beginning. It will be available there. Yep. So maybe first 5 years, it's not there in the small airports, and then it will come. So just an interesting thing that I did not see anyone look at in research. So we wanted to see the trades in that type of mission.
Okay, thank you. I was just wondering about your chain of thought there.
Okay, thank you. Let's move to the fourth presentation. The last presentation will be given by Professor Fabrizio Ponti. He had a bachelor and master degree from University of Bologna, a PhD from Polytechnic of Bari in 2000. He was assistant professor at the University of Bologna since 2000, and he became associate professor at the same university in 2007, and again is a full professor at the University of Bologna since 2018. The research interests of Fabrizio are solid rocket booster modeling, aerospike performance evaluation and modeling, electric propulsion system development and modeling, and gas turbine engine modeling and simulation. So the floor is yours.
Thank you for the nice presentation. As you understood, I'm a propulsive guy, so propulsion is what I deal with in my research. I can skip this presenter background and I will go directly to the introduction of my presentation of the work that I'm presenting you today. So, introduction is giving information that have been given many times this afternoon, so I will skip a bit. The only point that I want to highlight here is that if we are interested in both emissions in terms of CO2, but also in terms of NOx, the standard way of generating power, so through internal combustion engine, is not an option because we need to avoid NOx production. So we can reduce NOx with the internal combustion engine, but the best way to avoid this kind of emission is to use fuel cells. So this is why we focused our attention on proton exchange membrane fuel cell. That is what we use for power production. The top-level aircraft requirements that we considered is a cross-country mission that is obtained through a general aviation aircraft. The type of aircraft that we considered is a Cirrus SR-22 class. And you can see here in this slide the original aircraft requirements and characteristics compared with the new aircraft. So I'm going directly to the end of the presentation, so to the results. And what I will show into the presentation is how we obtain these results. And so what are the constraints that we consider, what are the, let's say, boundary conditions that we consider for this study, and then how we obtain this result. We considered both a fuel cell scenario and also a full electric system with batteries, but the results that I'm showing here are obtained with the fuel cell configuration for the aircraft, because for the battery, obviously, we have a lower range that can be obtained. Fuel cells, so what kind of fuel cells we considered? We consider high temperature proton exchange membrane because we think that in this way we can obtain a benefit in terms of heat exchange. And so what we try to do with our design is to obtain a design that is feasible within, let's say, 5 years time. And we know that high temperature fuel cells right now are not yet available for the aeronautic market. So they are not available right now for aircrafts. But since we think that in 5 years they could be available, we consider this kind of
of fuel cell technology. The conversion efficiency that we considered is 55%. It is quite high, but it is feasible with this kind of fuel cell design. And we also considered an average between the beginning of use of the fuel cell, so beginning of life, end of life for the fuel cell. Specific power is considered 2.5, that is a specific power just for the stack, because we are considering a balance of plant design within the approach that we developed and we are considering for our design. Then what else? We are considering gaseous, hydrogen is stored within tanks, but a high pressure tank with hydrogen in a gas form, so not liquid, because we want to consider a design that is robust also with respect to the airports that will not have the possibility to fuel with liquid hydrogen. The results that we show here have been evidenced by ZeroAvia, that is one of the manufacturers for high temperature fuel cells, and also by another manufacturer that I cannot disclose you here because it is not possible for me right now, but trust me, we have available this kind of information. So the higher operating temperatures, as I already said, has the advantage of a higher overall efficiency, first of all, but also in terms of balance of plant, we can consider some simplification because, for example, humidifiers can be avoided, are not strictly needed. Then the radiator downsizing has already been talked about. And then there is another advantage that is quite significant from my point of view, because you are more robust with respect to impurities that can be contained into the fuel. And so you are more robust with respect to impurities of hydrogen. Hydrogen storage, as already said, we considered a high pressure tank, 700 bar is what we considered. We think it is a technology that is already quite mature. Cooling is not required, at least this is what we think. You can perform a fast refueling and it is ready to use on board. The gravimetric efficiency is not high, we know that, and this will be the main cause for the weight and the initial weight of the aircraft increase with respect to the initial design. Sizing, we based our sizing on the cruise phase only. The assumption is that everything is not ideal, so both propeller, electric motor, inverter, so everything is not ideal, and we considered efficiencies for each component, and efficiency are based on, for example, a high voltage level that has been considered for the entire system, and so the numbers that you will see later on are based on these considerations. Another point is that we did not consider the cruising phase as the 100% power for the fuel cell, so we considered a sort of lower, so some sort of throttling for the fuel cell. This is because we wanted to use the full throttle only during the climbing, and because we wanted to keep some sort of backup source of power for emergency maneuvers and things like that. There are losses obviously related to the electrical supply line, chain, and a share of the available power from the fuel cell is used to drive the air supply, so the balance of plant and so compressor and so on. These are the equations, so I explained these equations, so these are here just to give you an idea of the numbering that is behind the words that I said. And so throttling is, for example, 86%. That is not much lower with respect to 100%, but it is somehow lower. And then the other numbers that are coming from the considerations that we did, as I already said, for example, for the high voltage that we considered for the design of the electric line. Then some numbering also for the sizing of the stack and the sizing of the batteries that we considered. Because we have batteries also when we have the fuel cell configuration, because batteries are used in order to provide the power that cannot be provided by the fuel cell during climbing, for example. Mission analysis is coming from an iterative loop because we have the initial requirements that are coming from the original aircraft. Then, since we are facing an increase in terms of mass and consequently an increase of power that is needed, we need to have a loop that is considering this increase of mass and power. Then we could we started effectively with the initial range, original range of the aircraft, but the problem is that if you do that, then you will obtain a mass that is very high with respect to the original design. And so what we did is that we repeated this loop many times, reducing step by step the range in order to obtain a range that is still somehow reasonable, while not increasing too much the total aircraft mass. And so the design that you already saw at the very beginning of the presentation is the result of this double loop. So there is the loop that is providing the mission profile and an external loop that is considering every time a different range in order to obtain a reasonable final design for the aircraft. So this is what I already said. The range is first of all set, and then we have the evaluation of the required power and the overall mass. Then the cruise speed is obtained with the balance between the aircraft characteristics and the mass that has to be lifted. And finally, considering the flight distance, so the range that has been set at the beginning, the cruise condition can convert the distance into a duration. And so in this way we can obtain this mission profile that is what has been considered for as the final, one of the final results that we obtained. Obviously, this mission profile here is what is required in terms of aircraft, and we have to think how to provide it. And so, as I already said, the cruise condition is obtained with a fuel cell that is run throttling it, and so without considering its full power, while full throttle, full power for the fuel cell is considered during the climbing and during the takeoff operations. And so you can see here that we need also some power coming from the batteries. And the design of the batteries has been obtained considering the energy density that has been shown in a previous slide. And so in this way we have the full mass of the aircraft and the complete design. One point now is that we have to locate somewhere the tanks that are quite large, since we are not using a liquid hydrogen but a gas hydrogen. So where should we place the tanks? So the idea is to consider not many, but not just one tank, but more than one. In particular, we are considering 4 tanks to be located behind the wings, and one spherical tank that is located within the main body of the aircraft. So 4 ellipsoidal tanks and 1 spherical tank. There is still some volume that is available for luggage within the cabin, but most of the volume that is available is occupied by the spherical tank. This is a possible configuration of the system. So you can see here there is the spherical tank and the ellipsoidal tank. We chose to have 4 of them because of the diameter that should not be too high because of the clearance with respect to the ground. So the choice has been forced by this. And the presence of these 4 external tanks required a revision of the aerodynamic characteristic of the aircraft, and in particular we estimated a 19% increase of the drag that is generated due to the presence of these tanks. A stability analysis has been run in order to verify that the change of the center of gravity does not affect the stability. And following the standard evaluations that can be run for this kind of aircraft, we verified that the configuration that we obtained is still stable. So it is possible to have to confirm stability for the aircraft. So for this stability evaluation, we considered obviously not only the addition of the tanks, but also the masses that are involved for the electric motor, the positioning of the fuel cell that I forgot to mention before, is thanks to the more compactness of the high temperature fuel cell, can be allocated here in the vein that is usually available for the internal combustion engine. So there is space enough for allocate the fuel cell. Then, once we have the total mass of the fuel cell, let's say, exercise that we did is to try to investigate what would be the range that we can obtain with the same mass, but using this time a battery only aircraft, so full electric aircraft, but using batteries. And what we obtain is that the range is reduced very much, from 500 to approximately 200. So the reduction is quite large in terms of range. And so this is done even considering an energy density that is significantly still reasonable, but significantly higher with respect to nowadays batteries. Because once again, as I already mentioned, we want to see what is the technology that hopefully will be available within a range of 5 years. So this is more or less the conclusion of my talk, and from what we saw, obviously fuel cells are preferable with respect to batteries. We obtained a design that is reducing the range from 800 to 500 nautical miles with an increase in terms of total initial mass of the aircraft. So there is something that has to be paid if you want to use fuel cell, and if you want to use a powertrain that is not producing emissions at all. And this is what we experienced. The storage has been considered through some sub-wing tanks and one larger tank that is spherical and within the aircraft body. And we considered also the stability of the aircraft, considering and evaluating that stability is still confirmed. This work has been developed within the MOST activity, that is the Sustainable Mobility National Research Center, that has been created within the funding that is coming from the European Union, that is very well known in Italy as PNRR. Thank you for your attention, and I'm here if you have any question or curiosity about what I showed you. Thank you.
Thanks, Fabrizio. First question.
Hi, thank you for the presentation. I had 2 questions, if time permits. First one is, how did you compute the aerodynamics of the aircraft? Because you mentioned an increase of 19% in the drag.
Yeah, it was a simulation that involved the entire body of the aircraft, and then we added the sub-wing tanks, and we consider what is the difference. And if you mean what is the software that we used Fluent.
Okay. And then for my second question, I noticed that despite the increase in max takeoff weight, the wing area stayed the same. Wouldn't that have any repercussion on the power required and low speed performances?
Yeah, there is a in the loop that is, outside the loop that I showed on the slide. It is considered that that effect, so the effect given by the larger request in terms of lift that requires more power, but has not been shown in the slide. So that is one loop of a larger loop that is outside.
Yours.
Yeah, thank you very much for your presentation. I was looking at your initial assumptions, etc. And in your presentation, I was missing a power loading diagram, a power loading against wing loading diagram. Did you do that analysis to see what was the limiting case?
Yeah, it has been done.
Because it looks like you used the cruise as the limiting case, but the consequence is that your takeoff distance is going to be enormous. It's gone up by 30% compared to the original. That limits you in your operations.
Yeah, I know that, but we decided to use the cruise and then to see what is the effect.
Okay, thanks.
Yeah, actually, the increase in the mass of the airplane the constraint concerning especially landing, maybe takeoff can be solved with a little bit of extra power. However, use size for cruise, so it's not the case. But however, the landing will be
we know that, but
not in line with the original aircraft.
it is not in line. I mean, it is an exercise that we did in order to see what is coming out, even with a fuel cell that is high temperature, and so that is beyond the actual.
Another question?
Yeah, nice work. So you use high temperature fuel cell or PEMFC chemistry. So first of all, is that chemistry available in literature? And secondly, usually they say that the power density is worse. The only gain you get is the higher temperature. So was that the case, and how much worse is it?
So from what we saw, the power density is worth going toward a high temperature fuel cell. So this answers the second question. The first one is the chemistry available. Yeah, there are some works that are available. Are manufacturer data available? Usually no. So each manufacturer is keeping data for their design strictly confidential. Nowadays, at least.
Other possible question?
If the chairman allows me a second question. You looked at battery energy density of 400 watt-hours per kilogram. That is rather optimistic, but is that at cell level or at pack level?
Okay, it is the global level.
Okay, then it's totally unrealistic.
Yeah, I know that.
Okay. However, the battery.
But let's say like this: even if we consider that level that is not realistic nowadays, the reduction in terms of range is so strong that I mean, it confirms once more that it is not feasible to run just a battery aircraft.
Also, maybe concerning consideration concerning the drag that you have estimated for the extra tank. Also, of course, you need to consider the drag for the cooling of the fuel cell. So
yeah, even if since we have we considered a high temperature fuel cell, the difference is not so high with respect to a standard engine, because the temperature is much higher. Sorry?
You can use the Meredith effect, you release the heat into a nozzle and add some
Yeah. Well, yeah, we did not consider that. We considered that when sizing the heat exchanger, we saw that since we have a much higher temperature, it is possible to keep the dimension of the heat exchanger more or less the same as the standard internal combustion engine for this application.
actually, the Meredith was used in Spitfire, so when they had very power, Mustang also. Yeah.
But not only that, but I just saw a presentation from DLR, this kind of additional bypass. They added heat exchanger, and the numbers show that it works. So even today, we saw that.
Other question? Other curiosity from my side is why did you consider that general aviation airplane, and considering that we have a national company which is very good and is Tecnam, you know?
We considered this aircraft because we received an input for this study that is coming from an external company, and they wanted to work on this aircraft. So,
just joke. If there are no questions, I thank Fabrizio for your
I thank you for
presentation,
your attention
and
involvement.
Actually, we will we will close this hydrogen number 3 session. Thank all of you for attending this interesting session with 4 presentations dealing with, of course, propulsion issues, but of course also implementing this propulsion, innovative propulsion challenges on airplanes, on configurations ranging from regional to the also general aviation market. So thanks all of you, and this ends today session, and there is the dinner at 7:30. So I think you know how to go there. Is on the indication on the program. Yeah. No, dinner is a reception. No, sorry, maybe not really a dinner, but do not expect too much. I don't know actually. Yeah.